what we'll look at now is a few different examples of question types that you might come across when it comes to electromagnetic induction. So basically, we'll run through basically key ideas in very brief terms, and then we will then look at different types of examples. So when it comes to electromagnetic induction, there are really only two main ideas that you really need to be aware of. One is Faraday's law, which basically relates the EMF induced to the changing magnetic flux. And in your formulas, you have it along these lines. Basically, that means the EMF induced is related to the rate of change of flux. And Lenz's law, in very short, simple terms, is basically it opposes the change. So of course, that's not the technical thing. Lenz's law in words is a bit longer than that. But you can think of it as basically this negative sign here. It's giving you the direction of the EMF is going to go against the change in flux. If change in flux is positive, the EMF is negative. If the change in flux is negative, EMF is positive. That's basically the key idea. Now, whenever you have an electromagnetic induction, you always require a change in flux. And this can be achieved in many different ways. So we're going to be looking at questions with each of these types, but we could, for example, move a magnet with a coil. So that's sort of one situation we might deal with. We might deal with, for example, the idea of changing the shape of a coil in a magnetic field. We can look at variations of this. We could look at varying the magnetic field. Or we could look at very similar ideas to that, which is changing the current, which increases or decreases the magnetic field. And we'll take a look at each of these in turn. So let's consider firstly a simple scenario where you have a coil and you've got a magnet moving. So over here, we have 4 examples of magnets and coils moving towards or away from each other. So in this case, we'll assume our coil is stationary and our magnets are moving. So in this case, I've got the north pole of a magnet moving toward the coil. In this case, I've got the north pole moving out, and I'm just changing it the other way with the south pole moving in and south pole moving out. So of course, be aware that I could, of course, have done it on the left-hand side. I've just chosen to do it on the right-hand side here. Now, when this magnet moves, what's going to happen is that it's going to cause this coil to experience a change in flux. Because after all, remember a magnet, do it in sort of green here, a magnet creates a magnetic field like this. Won't draw in all the lines. So as it gets closer, more of these magnetic flux lines will cross the coil. Okay? And then you can get all wrapped up in all your, okay, so it generates an EMF, and so it causes a current, which causes a magnetic field, and so on and so on and so on. But for doing these questions, we're just trying to figure out, okay, what's going to happen? Is it going to go from A to B or B to A? Just think of it as I said earlier, it always wants to oppose. So if you want to push the North Pole in, what that means is that this coil wants to repel the North Pole. So your action is North Pole to the left. The system, if you like, or Lenz's law, if you like, will tell you that you will want to push the North Pole to the right. You will want to repel the North Pole. Now, the only way the system can really repel the North Pole is to make its own North Pole. So it has the capability to make a North Pole. It can make a North Pole there. Now, if it makes a North Pole here, because after all, it can get current to flow, that will repel this North Pole. So to make a North Pole here, what you would then need to do is then use your right-hand grip rule all the way from before. Your right-hand grip rule needs you to have your solenoid with your thumb to the right and with your hands wrapped around your pen, meaning that will tell you your current will flow this way. So that means when you move the North Pole here towards the left, your current, well, your system or this coil will try to repel that to resist the change. The only way to get a North Pole over here means that by Lenz's law, the current will flow this way around the coil, which means when we ask for in exam questions, we're normally asking about the direction from the galvanometer. Pay special attention to this. A lot of students will think that this flows from A to B, and it does, going that way. But through the galvanometer, we're saying that it flows from B to A. So be very careful about that. In this case, we've got the North Pole going away. So the action in this case is the North Pole moving away. That's the change. And so Lenz's law will say what will happen is you want to oppose that. So you want to, in this case, pull the North Pole to the left, which in this case means attraction. So the only way to attract the North Pole, as you might be able to guess, is to make a South Pole. So to make a South Pole, well, again, your right-hand grip rule comes into play. Your right-hand grip rule will then need to make a North Pole on the left. And so with your right-hand grip rule with the North Pole on the left, you'll find that what happens now is your thumb is on the left, the current would have to flow this way, which, as you would expect, is in the opposite direction to the one we just did. And that then means the current would flow left to right through the galvanometer here. Applying very similar logic here, if we've got the South Pole moving in, what we would want to do is we would oppose it, we would repel it with a South Pole. If you need a South Pole on the right, that means you would need a North Pole on the left. And if you have a North Pole on the left, you will use, again, your right-hand grip rule to confirm that your current would indeed flow this way. Very similarly here, you've got a South Pole going to the right. If you have a South Pole going away, remember, they don't want it to change. They want the South Pole to stay. So for the South Pole to stay, you want to pull it back in. That means you need a North Pole to try to do that. To get a North Pole on that side, that means you'll end up using your right-hand grip rule to get the current flowing this way. And that will then result in a flow from right to left. And so with these 4 examples, you can see that pushing the North Pole inward is going to result in the same effect as the pushing the South Pole outward. And taking away the North Pole is going to result in the same effect as pushing the South Pole inward. Yeah. So you can, of course, do the same thing on the left-hand side. I won't do that here because I think this is probably sufficient exercise for you there. But I want you to note, when you're doing questions like this, you really want to pay attention to the way the coil is coiled, as well as what your question is asking. So pay attention to the way the coil is coiled and the direction of the current. Refer to question. What do I mean by that? Well, compare these 2 questions. This question has a North Pole approaching the coil from the left. This question has a North Pole approaching the coil from the left. But if you look carefully, the coil is wrapped differently. See, on this left-hand side, the coil is wrapped in front, on our side first, and then beyond. So in other words, if you're looking at it from the point of view, if you're looking at it from this point of view, then you're seeing the coil ring wrapped anti-clockwise, right? You're seeing the coil kind of going like so for this one. Firstly, on the right, and then to the left and wrap around. With this one, though, it's actually wrapped behind first and then going to the right. So with this one, you're actually seeing it go like this. And that is actually a critical difference. Because now when you do this, when the North Pole is coming in, both coils we'll want to repel this north pole, and we'll want to create a north pole on the left. But using a right-hand grip rule, a north pole on the left would result in the current going like this. That's the current on the left-hand side. But for this one, to get the north one on the left, that would actually result in the current going like this. So you can see that when this gets closer, this north pole will be created, and you'll end up with the current flowing here from the right to left. In this case, the north pole gets closer, means that they're all going to flow this way using a right-hand grip rule. That, of course, means that these parts in front of you facing you will be going up to generate the north pole on the left. But because it's wrapped differently, it's actually going to be flowing left to right. And so pay close attention to the direction of I, because in this case, we would be saying that it will be going from, well, A to B, but in this case, it will be going from B to A. And be very careful as well. When you're talking about the direction of the current, it is usually at the galvanometer. It is not usually at the rest of the coil, so we're not talking about A wrap around to B, but rather at this point, it's B to A. So those are the really key things you probably want to watch out for that sort of question. So before we get to shapes, the other common scenario is considering when what happens when you've got a coil such as this, and it's going to move through a magnetic field. So that's what this crosses are meant to represent. And we're basically consider the situation when, okay, you've got this coil and it moves, let's say at constant speed, and it just moves at constant speed through this magnetic field. Now, probably quite clear that before this point, there's no flux. That should hopefully be clear. And then as it enters, it's going to experience a change in flux because, well, right at this particular moment in time, it's, well, got a flux of 2. And as it moves into the page, and as it goes further in to the magnetic field, it's now got a flux of 4. So at this particular point, we'll just say it's got a flux of 4 into the page, which we'll just treat as positive. And then over here, because it's a constant magnetic field, you'll assume it's more or less the same. So all the way up to here as well, the flux will be 4 into the page. But of course, now that it's going to get towards the end of this magnetic field, when it exits, it's now going to become 2. And when it exits fully, it's going to become 0. So at this point here, we're saying the flux is now 0. So if you consider the motion of this wire or this coil through this magnetic field, then it experiences a change in flux both on entry and exit. And that's when we get our induced current and electromotive force. So this is when you get a change in flux occurring. And this also is when you get a change in flux occurring. But it's important to recognize what the direction of this change in flux. So you've gone from 0 to 4 into the page. So the change in flux is into the page. So let's just focus on this starting point for now. You've got from nothing to into the page. Now remember, this is the change. The change is going into the page. And by Lenz's law says it doesn't like change. So it will oppose it. So to oppose into the page, it needs to create out of the page. And, well, you've got a coil, right? It's a simple coil over here. To generate out of the page, and the thing with coils, remember, you only care about the inside of the coil. What's important is the inside of the coil and not the outside. So we want the inside of the coil to generate a magnetic field in terms of the opposition. You want it to be out of the page, like so. Okay. Not very uniform, but the idea is the direction. Okay, the direction is what matters. And then to then decide which way the current would flow to make sure that it goes out of the page, we'll again use your right-hand grip rule. Your right-hand grip rule would tell you that to generate, for a coil like this, to generate an outside of the page inside the coil, it would have to flow in an anti-clockwise direction. So what that means is that for this coil to basically what that means is then as this coil enters, right? Nothing before, but as it enters, it's actually going to get this anti-clockwise current flowing through it. So result, current anti-clockwise. Now, of course, we can now examine what happens on exit. So on the way in, it's going to be clockwise. On the way in, anti-clockwise. In the middle, there's no change in flux, as you can see, so nothing. It's the change in flux that matters, but on the way out, something's going to happen. So let's see what happens. You're going to go with a change in flux from 4 in to 0. To go from into to 0, that means the change in flux is out of the page. That means the opposition, you want to oppose the change, so you must generate into the page. And I mean, if out of the page is going to be anti-clockwise, you can probably guess that into the page is going to be clockwise, but we'll just check that out. Into the page, get your thumb ready, thumb into the page, your fingers will wrap around in the clockwise direction, meaning that that's what would need to happen. So you'll end up with it having in a clockwise direction as it goes outside the page, out of the magnetic field. So when you're dealing with questions with regards to coils, really focus on the fact that, remember, you're not dealing about the outside of the coil, you're thinking about the inside of the coil. And as per usual, you want to deal with the change in flux, and you want to go the opposite to that. We'll now extend that to changing shapes of the coil inside a magnetic field. So we now have the situation where we've got this coil, which is a circle. And in this circle, it's basically, well, in a magnetic field. And as you would expect, because it's a coil in a magnetic field, it's got some flux. Now, what we're going to then do is then we're going to, okay, change the shape of this coil. So we could, for example, squish it like so. Okay. Coils are made of wire. Wires can often be flexible. I might not be so extreme. Maybe I could just make it like this, for example. But the fact of the matter is, I can change the shape of this coil. So I start like this. So when it's a circle, this is our start. We can count up the flux inside the coil. Now the flux, if you just treat each one as 1, we don't really care about the unit here. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can say the flux is 9 into the page. Now I'm going to change the shape, and let's say I change it to something like this, hypothetically. So now it's been squashed to an oval shape, a smaller oval shape in this case. And then the flux now, if you count it, there's only 3. Whenever you're doing questions like this, what you need to ask yourself is there a change in flux before and after? And if you're not sure, just check out and work out the flux before and work out the flux after. Now the flux was 9 into the page before, and the flux after is 3 into the page. If you have trouble working out which way it is, just remember the way you get change in flux, as with change in anything, is the flux after, or final, minus flux before, or initial. So that's basically 3 into minus 9 into, which is, if you like, negative 6 into, which is 6 out of the page. So hopefully that gives you a clear idea of how to approach working out change in flux. If you understand how to do it, you don't need to necessarily go through all those steps. But basically, you're going from 9 into the page to 3 out of the page into the page, which means the change is out of the page. All right. And that change is what we care about. So when it comes to electromagnetic induction, if the change is 6 out of the page, then we must oppose that. And we must therefore make into the page. Basically, think of it like this, right? Before there was 9. Now there's 3. The way we would try to get back to what it was is to add, if possible, 6 more. Now that's not going to happen, but we're going to try, or more properly, the wire will try, the coil will try, right? So in other words, you're just going to have to think of what the change was. There used to be 9 members in the group, if you like, right? Flux was 9 before, 9 in the circle, 9 in the coil, in the inner group. They lost members, so they're going to look for new members. These members were into the page, so you need to try and make into the page. You're always trying to get back what you were, okay? So for them to try and get back, then basically, how do you make into the page? Well, if you want to try and make into the page, this is where your right-hand grip rule comes in, all right? To make your right-hand grip rule into the page, thumb into the page, your fingers will wrap around. That then means that this will get an induced current that will be clockwise. Of course, if I did it the other way, if I had not had made it smaller, all right, if I made it bigger, then it would be anti-clockwise, all right. We'll now take a look at this example where we're going to look at this coil, which is placed next to a wire which carries current. But this current is changing. In this case, we're saying it's increasing. And basically, due to this increasing current, there's going to be an induced current in this coil, and we're going to work out what direction that is in. So here's the setup. You have a wire carrying current, and this current is increasing. Now, we'll run through this one in a bit more detail, and then there's a few more examples that will be very similar to this. But what you should be aware of is if you have a wire that's carrying current, then this current creates a magnetic field. And we can actually work out the strength of this. You can check our previous work, but this magnetic field is equal to some constant times I over D. For our purposes here, the actual number is not important. For our purposes here, what's important is the direction. So if you recognize that the current is going downward, then we would apply the right-hand grip rule, and we would then recognize that this is only a 2D representation of what's actually in 3D. So if your current is going down, your magnetic field lines that this current creates would wrap sort of, in this sort of direction around the wire. In other words, viewed from the bottom, it's going to be going anti-clockwise. And the result of that means that on the right side of the wire, which we do not care about, it's going to go out of the page. But the part of the wire we do care about, which is on the left, it's actually going to go into the page. You don't really need all those crosses. What's more importantly for us is that it's going to go into the page. So it'll create a magnetic field, which for our coil, which is to the left of this wire, it will create a magnetic field that is into the page at the coil. Remember, when we're looking at induced currents with coils, we only care about the inside of the coil. And by that, I mean this area here. We don't care about the outside of the coil. We care about the inside of the coil always. Okay. So now, what's our change? Our change is that the current is increasing. So as the current is increasing, you can quite clearly see, just based on your general knowledge from your earlier work here, that if the current is increasing, that means the magnetic field that this current creates will get stronger. And you can see it from that relationship there. Again, for this question, the number is not important. The relationship is, though, not the number, but the relationship. So as the current goes up, we know the magnetic field goes up. So basically, we're saying that the magnetic field is going to get stronger. Which means, if you think about it before the magnetic field in flux inside the coil is into the page. And we can make up some number, like 5. Doesn't really matter to us what the number was. But after, the flux is still into the page, but bigger. So let's go with 10. Doesn't really matter. And for us, what's important is the change. So the change in flux, remember, is after minus initial. So in this case, you've just gone from 5 into the page into 10 into the page. So it's 5 into the page. Now again, unless you're doing calculations for EMF, that number doesn't matter. When we're just working out direction, what matters is the direction. And therefore, the change is into the page. Again, think of it like a club. There were less people in the club before. Now that there are more people in the club wants to get rid of some members. Too many people in here. Okay, it wants to get rid of some. How does it do that? Well, it's got to expel some out. So it's going to cancel the membership of some of them. So, you know, you're going to bounce them out. So you now want to create anti-members, if you like. You want to now create out of the page. So to oppose that, you want to create out of the page. And to create out of the page, then again, using a right-hand grip rule, that basically means you're going to get a induced current that would flow anti-clockwise here. The anti-clockwise using a right-hand grip rule will create a magnetic flux out of the page, which is exactly what you need. So the result is induced current that will be anti-clockwise. So let's reiterate what we're doing here and then run through a very few similar examples here. Firstly, in this case, think of what's happening with the current. The current creates a magnetic field. In this case, because the current is increasing, the magnetic field is getting stronger. We then need to use the right-hand grip rule to work out what's happening with the magnetic field around the wire. And then we've worked out that in this particular case, for the coil in question, given its placement, it's getting a magnetic field into the page. So as it's getting magnetic field into the page, the stronger, and as it's getting stronger, the change is more into the page, which means it wants to go against that. So it wants to create out of the page, which means it's going to flow in an anti-clockwise direction. There are some shortcuts we can use, but this is the sort of fundamental ways to sort of think about it. All right, so now let's give you a few more examples of this. just do them in rapid fire succession. So in this case, we have a current flowing to the left. So this current flowing to the left then means, using your right-hand grip rule, that your thumb is pointing to the left, your fingers will wrap around your pen, and so you'll end up with a magnetic field that's going into the page at the top and out of the page at the bottom. Remember, out of the page at the bottom is not important. So, but that is the magnetic field created by this wire. Once we know what's created by this wire, we're now able to take into account the fact that it's decreasing. So it's decreasing. That means, if you like, the flux inside is decreasing. It's losing members, right? It's losing some. So if you think of it like a club, if you like, it doesn't want the membership to change. It wants to at least be, it wants to maintain stable membership. So it wants to create into the page because it's, well, the outside magnetic field is not maintaining that. So it wants to maintain that. And to get into the page using a right-hand grip rule, that means you'll get current flowing clockwise. In this case, you've got a current flowing to the left, kind of like this. So if you use a right-hand grip rule, you'll again find below the wire, it's going to be out of the page. Above the wire, it's going to be into the page. What's important for us here, I'm going to stop drawing both sides. What's important for us here is the into out of the page, below the wire. So now they've got out of the page, but it is increasing. So as it's increasing, that means the club is getting more and more members, right? Because it's getting stronger. The club wants to stay exclusive. It doesn't want that many members. So it needs to cancel out some members, right? It needs to kind of, the members here are out of the page. So it needs to sort of get some into the page to cancel some out. So to get this into the page, what then happens with your right-hand grip rule is your thumb goes into the page, your fingers wrap around in a clockwise direction, and that gives you, in this case, very similar to the one on the left, because you want to create into the page, it will result in a clockwise direction. Okay, two more questions here. We've got a current going up. Current going up will, of course, create a magnetic field, which will create one into the page on the right. Once it creates an into the page on the right, we then need to take into account that it is decreasing, which means it is losing members, which means this coil wants to make more into the page. And you've seen this many times before. Using a right-hand grip rule again, that coincidentally, again, will be clockwise. On this side, what we have here is you've got a wire going up. A wire going up will again create into the page on the right. But for our purposes, what's important here is on the left, which is an out of the page scenario. Because it's increasing, that means it's getting more members, right? The magnetic field is getting stronger. It's putting more and more magnetic flux in there, which the core doesn't like. It's got to get rid of some. Ideally, cancel out so there's no change. So now it's going to try and create again and into the page again, right? And that would then mean anti-clockwise, I should say, for this one. It will create it like so, and that will result in an anti-clockwise induced current. So we can obviously try all sorts of combinations of current increasing or decreasing and the wires being placed on different locations relative to the coil. But the way you work through it is exactly the same. Now, I'm now going to give you a sort of So we're going to give you a sort of shortcut, if you like, that you can use for multiple choice questions and things like that. That could be useful. The explanation we've done here is the fundamental reasons behind why. We've covered all the reasons, right, with all the different rules and so forth. However, just like how with certain times you want to save time. So with this one, we kind of just didn't really get into all the details. We just told you, okay, North Pole wants to go in, create a North Pole to repel, that sort of idea. We'll give you a very similar situation here. Basically, the system, we've explained all of these, and these are all the right answers, but you can see the current is flowing down and it's increasing. So if you take a look at the whole thing as a whole, just take a look at, let's say, this section, which I'm going to do in yellow. If the current is going to go down, basically, we don't want that to happen. Remember, we always want to oppose the change. So to oppose current going down, what has the coil done? It has caused the current to flow up. At the closest possible point, close to the wire, it's gone against it. Okay, that's not a proper full-on explanation. This is the full-on proper explanation. But if you're having trouble following that and that takes too long, then these are shortcuts that you can use, although of course it's not a full-on proper explanation. And we'll see how that works with our 4 example questions. See, you've got here current decreasing. So you've got current going to the left, but it's getting weaker. So what has the coil done? Obviously it's circular, so we've got to look at the point that's closest to the wire. It has boosted it. It's trying to get it back. Same thing here. You've got current increasing to the left. So what has the coil done? It's gone, well, we don't want that increased current. We want to sort of counteract it. We want to get rid of it. Over here, you've got a current going up and it's decreasing. So what's happened? The coil has boosted it. So the induced current plus the original current is as close to what it was before as possible. Over here, we've got an increasing current. So what has the coil done? It's gone against it. If you don't understand the shortcut, then I recommend don't use the shortcut. The shortcut is there only sort of as an aid, but in terms of actually properly explaining why these things occur, you should be going through each and every step as we've discussed there. Now, there are more complex questions that can be available, but this really covers the significant types. And anything more than this would often involve sort of more than one type mixed together, like turning a signal on and off. So that's basically how you do the simple type version of these questions.